Hi, I'm Choi um, um, in Earth and Atmospheric Science at Georgia Tech. I just came to Korea to start a new postdoc position in KIOST. Today I'm going to talk about dispersion statistics in Lake Michigan and the Gulf of Mexico. There's no relevance between the Lake Michigan and the Gulf of Mexico. I put those two different environments in this talk because those areas were the study area in my PhD, and so I want to share with you about the dispersion study in those areas. So motivation. So the ultimate goal of this dispersion study is to provide useful information to the decision makers when oil spill like accident happen. So when it happens, they may have following questions, such as where will it go and how fast will it go and how fast will it spread, and what kind of physics will be linked to it. So, so this figure is the oil location when BP oil spill happened in 2010. So first figure shows the oil location in first month, and this shows the oil location in second month. So in first month, those kind of oil attacked in Louisiana area, and second month this oil attacked in northern Florida. So if the decision maker know about the information about where this oil go and how fast it will reach to those areas, it will be great for them to prepare some strategy to prevent some damage caused by this oil spill. So this is outline. So first, I'm going to introduce some quantification method for vertical mixing and horizontal dispersion, and followed by the physical processes in Lake Michigan and the Gulf of Mexico that may associate with the dispersion statistics, and followed by dispersion statistic in Lake Michigan and the Gulf of Mexico. And finally, I'm going to introduce a satellite application for real-time contaminant monitoring and short-term forecasting using Lagrangian coherent structure. So last two part is kind of the future work for me. I'm going to do this work in KIOST. So let's talk about vertical mixing parameterization. So we can calculate vertical diffusivity Kg from the dye experiment such as rhodiamine WT or SF6 or scalar simulation. So you need a two profile, like an initial concentration profile in vertical direction and final concentration profile. So you can easily calculate the vertical diffusivity using this equation. And also, if you run the simulation like a scalar simulation, you can have three-dimensional concentration. So you can calculate the variance using the second moment of the concentration, 3D concentration, and then you can easily calculate the vertical diffusivity. Now let's talk about the horizontal dispersion. So most popular way is to use the relative dispersion. So it measures the separation distance R with. So it's defined by the mean square of separation distance R in all pairs. And after we get the R square, we can calculate the horizontal diffusivity using this equation. So from those two equations, we can get two graphs. One shows the relationship between R square versus time, and the other shows the relationship between K versus R. So we can get the fitting parameter, fitting exponent, and M and N. So if M is equal to 1, we can say this is diffusion, and corresponding component exponent n is 0. And if m is equal to 2, we say this is ballistic dispersion. If m is 3, we can say this is this dispersion is associated with the Richardson dispersion or shear dispersion. So corresponding exponent here is 4/3. So this shows also Richardson dispersion. But this relative dispersion is challenged and criticized because it cannot show the effect of certain size of eddy or certain certain length scale, because it's defined by the mean square average of R. So some pair can have small r, and some pair may have big R. So it's kind of average of all kinds of the eddy size. So it's hard to show the effect of certain size of eddy. So in order to overcome that, we use finite size Lyapunov exponent. So it measures, it takes from separation distance delta to separation distance 1.2 delta. So using this equation, we can calculate the FSLE and the separation distance delta, and we can calculate the fitting parameter m. If m is -2, it associated with diffusion. If it is -1, it is associated with shear dispersion. If the exponent is -2/3, we said the dispersion is Richardson dispersion. And if the Sohmer scale process are strong, we get the -1/2. And if this exponent is 0, we can say the dispersion is associated with the exponential dispersion. So in the previous two slides, I talked about the quantification of particle dispersion. These slides talk about quantification of scalar dispersion. So the variance ij square can be calculated from variance sigma I and sigma j, which are the standard deviation of the concentration in major and minor direction. And sigma I and sigma j can be calculated from the eigenvalue decomposition using covariant matrix. And finally, we can calculate the horizontal diffusivity. So this is an example of the standard deviation in major and minor direction in real dye concentration map. So let's talk more about the horizontal diffusivity. So as time goes, the dye patch increases. The size of dye patch increases. Also, the size of the drifter cluster increases. So if we plot the relationship between the sigma square variance versus time, actually this slope is dispersion coefficient k. So if the exponent is 1, we can say this is a normal diffusion. And if the exponent is less than 1, we can say this is subdiffusion. If this exponent is larger than 1, it is a superdiffusion. And superdiffusion and subdiffusion are the anomalous diffusion. So the normal diffusion is corresponding to the scale independent constant k, because this k does not change with the size of the dye patch or size of the drifter cluster. But if you see the superdiffusion, k is scale dependent. That means dispersion coefficient k increases with the size of the drifter cluster or size of the dye patch. If the exponent is 3 here and 4/3 here, we can say this is Richardson dispersion. So Richardson dispersion is found by Richardson in 1926. He was a meteorologist, so he had a lot of chance to observe the sky and air. He observed the volcanic ash and some cyclone in the sky, and also he observed the balloons in the air. And he calculated horizontal diffusivity and cluster size from this phenomenon. Then he plot the relationship between the dispersion coefficient K and L. And he found the exponent 4/3. This is a Richardson dispersion. And later time, this Richardson dispersion is found in the ocean by Okubo in 1971. This also shows a Richardson dispersion. So Richardson dispersion does not happen always. It happens when the dye patch, size of dye patch or size of drifter cluster is comparable to the size of eddy in inertial subrange, where the slope is minus 5/3 in kinetic energy spectra. So this is Richardson dispersion. So when the dye patch, the size of dye patch is comparable to the dissipation scale, then it shows a diffusion, so the exponent is 1. If the size of dye patch is larger than the integral scale, it becomes the diffusive behavior again. So let's talk about the physical processes in Lake Michigan and the Gulf of Mexico. I will show you only some important physical process that can be related to the dispersion statistic. So this is one physical process in Lake Michigan. Can be found in the summertime in the center of the lake. So this is actually the measurement. This is top surface and this is the lake bottom. So this near inertia internal waves shows clockwise rotating with a near inertia period of 17.5 hours. And it has a strong shear near surface and the thermocline. And this measurement was made at this location at the center of southern basin. And this is important physical process in the Gulf of Mexico. And this is a sawmill scale processes. That size, the time scale is order of 1 day, and horizontal length scale is order of 1 kilometer, and vertical length scale is order of 100 meter. So this is a kind of example of sawmill scale processes. So strength of sawmill scale processes has a seasonal dependence. So during the winter time, the mixed layer thickness is maximized. So the sawmill scale process become maximized. And if the riverine forcing is strong, especially in the Gulf of Mexico, there is some freshwater influx from the Mississippi River that increase the gradient, density gradient, and that result in some instability at the surface. That result in the strong sawmill scale processes. So I'm going to show you some dispersion statistics in the Lake Michigan and the Gulf of Mexico using some field experiment and some numerical result. So this slide shows the, I'm going to use 6 surface drifter and 11 kilometer of rhodamine dye released at the surface at the same time at the center of the southern Lake Michigan. So at that time there was a strong near inertial wave. We observed that, and then the wind was almost 0. And we tracked the drifters and the dye patch for 1 day. So this is almost start of the drifter and dye patch. And we tracked almost 1 day. So gray bar shows the size of drifter cluster, and black bar shows the size of dye patch. And this is dye, and this small circle indicate drifters. So from this figure, you can easily recognize there's a big difference between the drifter dispersion and dye dispersion for one day. So using those data, we can plot some dispersion plot, variance versus time. So black line shows the dye dispersion, and the red line shows the drifter dispersion. So if you calculate dispersion coefficient K, dye has almost 5 meters square per second, and drifter shows 0.1 meters square per second. So dye dispersion is 50 times faster than drifter dispersion in one day. And this can be explained by the shear, strong vertical shear induced by near inertial internal wave. For drifter, they remain at the surface, so they cannot feel the vertical shear induced by near inertial internal wave. But dye, they go to downward, so they can easily feel the vertical shear induced by near inertial internal wave. That can explain the difference between dye dispersion and drifter dispersion. And in this slide, I'm going to compare the drifter in Lake Michigan and drifter in Gulf of Mexico. So left panel shows the drifter dispersion in Lake Michigan. So we used the 6 drifters, and we released them at the center of Lake Michigan. Because of the strong near inertial wave, they just make a circle and make some oscillation. And as they approach to the near shore, the near inertia effect is weakened. And right panel shows the drifters in the Gulf of Mexico. We released 90 drifters, almost same time, like July 2012. And we released them at the same location where the Deepwater Horizon oil spill happened in 2010. So in this time period, we also found a strong near inertia wave, and we also found very strong submetric processes. So the green line shows the trajectory of one drifters, and I make out the red dot every day. So using those using those data, I'm going to show you the dispersion statistic. So the black line shows the Gulf of Mexico drifter, and the red line shows the Lake Michigan drifters. So left panel shows the variance versus time, and right panel shows the dispersion coefficients K versus cluster size. So the point is there's a big difference between the dispersion in Lake Michigan and the Gulf of Mexico. So we in both environments, we found very strong near inertial waves, but we found very strong submetric processes in the Gulf of Mexico. So in order to explain this gap, we can use these submetric processes that make the dispersion in the Gulf of Mexico very active. And this slide shows the scalar dispersion in the Gulf of Mexico. So we released a dye at the same location of BP oil spill at 1,000-meter depths. So we tried many different schemes, like different horizontal resolution and different vertical number of layer, and different vertical mixing scheme and different advection scheme. So we want to find a better configuration that can result in the more realistic the dispersion coefficient. That's why we did a lot of we tried a lot of cases. So we release a dye from here, the location of BP oil spill, at 1,000 meter depths. So let's look at horizontal dispersion. This is the vertically integrated dye concentration at 4 months after release. So generally, as we increase the horizontal resolution, and also as we increase the vertical resolution, the vertical horizontal diffusivity decreases. And even though we release a dye at 1,000 meter depths, it roughly follows the Richardson dispersion for all cases. And now let's look at the vertical mixing. So this shows the same story. If we increase the vertical resolution and also if we increase the horizontal resolution, the vertical diffusivity kg decreases. So some lesson from these simulations, we found the choice of vertical mixing scheme is insensitive to the kg. So we tried Mellow Yamada 2.5 and we also tried the KPP vertical mixing scheme, but we got almost same kg. And the choice of tracer advection scheme matters. We tried 2 advection scheme. One is MP data and the other is split up the advection scheme. But there are big difference between in the vertical diffusivity. So if we use the advection scheme of the split up, we got much less diffusivity. So the choice of tracer advection scheme is really important. And as we increase the number of vertical layer and the horizontal resolution, that strongly affect the vertical distribution of tracer. So that resulting in smaller vertical diffusivity. But the vertical diffusivity from the old simulation is still very larger, like order of magnitude larger than observation. So this result at least show us what's the better configuration to get a realistic the vertical diffusivity. I mean that close to the real value. So this slide shows the relative dispersion using the simulated particle in the northern Gulf of Mexico in summer and winter time. So this red line shows the summer and this blue line shows the winter. And there are 3 different initial separation distance, 2, 6, 30. And one point is stronger relative dispersion found in the winter time. That means we have more wind in the winter time and we have more stronger submersible process in the winter time. So that may cause a stronger relative dispersion. And the other thing to notice is as we increase the initial separation distance, it takes shorter time to reach diffusive stage. So for example, if we use the initial separation distance 2 kilometers, it can be easily associated with some eddy in the inertial subrange. That's why we see the slope -3 for if we use the separation distance 2 kilometers. But if we use a larger separation distance like 30, it takes a shorter time to reach diffusive region because this 30 kilometers may be larger than the eddy in the inertial subrange. So that's why it's easily associated with the eddy larger than the inertial subrange. That's why it's it reaches diffusive region very fast. This shows the finite side Lyapunov exponent for the summer and winter time. So the red is February and the blue is August, and the solid line shows the FSLA without any subgrid parameterization or diffusion. So the one point is stronger FSLE found in the winter time. That means it takes shorter time for the particle to be separated in the winter time. And the other point is this blue line is actually the observation from fieldwork. And there is a very big gap between the observation and simulation. So we tried to add some subgrid parameterization, like adding diffusion here. So we got this, I think it's better than this line, but it reached to the slope of -1, which means that corresponds to the shear flow dispersion. But actually the observation that shows -2/3, that is Richardson dispersion. So it seems like we need a better subgrid parameterization. So there's a lot to improve our simulation. So I'm going to show you the Scalar application for real-time contaminant monitoring and short-term forecasting using Lagrangian coherent structure. So Scalar is a really powerful tool to detect the biological and anthropogenic contaminants. So in left plot, it is red tide captured by the satellite, and right plot shows the oil spill. It is Taean Peninsula. Its oil spill occurred in 2007, and this is the image captured by satellite when the BP oil spill happened in 2010. And this is a sargassum captured by the satellite. So 1 month ago, like 15 days ago. So satellite is a really powerful tool to detect contaminants and monitor the contaminant, and eventually we want to prevent some damage from this kind of contaminants. So that's why we want to use satellite information. So this is a schematic kind of shows how we use satellite information to predict contaminant movement. So we can have some sea surface temperature and sea surface salinity information from the satellite. Also, we can get the sea surface from satellite, and we put those kind of data into the ocean modeling through the data simulation to get better result. And we can provide those oil area information to the pollution modeling. And this, the information got from the satellite can be an initial condition for the pollution modeling. So after we perform the parameterization, like wind parameterization, turbulent parameterization, and after we consider the pollution property, we can get accurate pollution forecast. So one example of pollution modeling is using Lagrangian coherent structure. So this plot shows some article captured from the New York Times in 2009. The title of the article is A Moving Boundary. So Lagrangian coherent structure partitions the flow field into the regions that have same fate and same dispersion rate. For example, if particle is dropped here, so the particle dropped here have the same fate. Or if particle is dropped here, the particle dropped in this area have the same fate, same dispersion rate. So for example, there's no material transport between this region and this region. So this kind of is an invisible barrier. So this kind of map can be calculated from the finite size Lyapunov exponent or finite time Lyapunov exponent. So this kind of the map is important because when the oil spill happens, we can easily predict where the particle goes, where the oil goes. So for example, if the oil is dropped here, this oil may reach this beach in soon. Or if the oil dropped here, it can reach this beach in a short time. So this kind of the method can be used to predict the movement of the contaminants. So this was outline, and I can mainly divide this outline into two parts. So first, three parts, like a quantification of vertical mixing and horizontal dispersion, and physical process and dispersion statistic. It's kind of efforts to answer those two questions. How fast will it spread, and what kind of physics will be linked to it? So this kind of things is a scientific question. So, but I mean the decision maker does not want to know about physical process and some kind of the spreading rate. This is the kind of the question our scientists have, and the other two part is the answer. Is the answer from this question the decision maker can have. But we need some balance study. For example, in order to get the output of simulation, we need to validate our model. So we need to know about the mixing coefficient from the observation. That's why we need this kind of things to make the simulation right. Also, in order to do parameterization right, we need to understand the physical process. So these kind of things should be balanced in order to make accurate the prediction of contaminants. So this is all I have.